NanoHub U, online instruction.
Hey everyone, welcome to lecture 114. We already talked about how the photonic crystal band structures look, but we didn't explain in a lot of detail how do we actually do the calculation. So we do know that it's based on the Maxwell's eigenproblem. In case you forgot, the Maxwell's eigenproblem is presented here. This is essentially the same as what we had before, just written in new notation, basically ket notation, so quantum mechanical type calculation. And you can actually see very easily that we can expand H into a set of plane waves based on our block wave solution. And so then we would define the operator on the left-hand side as AK, and then it's basically defined like this, and then we get omega over c squared in front of HK. And now we need to choose a basis for HK. And so without necessarily explicitly saying that HK has to be in a Fourier basis, we just say that we choose a basis that's orthonormal, which means that if you have two different basis elements, HKN and HKM, then we can basically say that they're going to give us an inner product of 1 if and only if n equals m. And then we can then expand H field in this basis, whether it's Fourier or another type of basis, such that HK is the sum over HM times BM. So it's a linear combination. And then that gives rise to a linear algebra problem, which is the generalized eigenproblem that AH equals omega over c squared BH, where B is a very simple auxiliary matrix. And then if we think about this problem, we have a very practical challenge, which is just how do we solve it as efficiently as possible. The first approach, the power method, would allow us to get a single eigenproblem or eigenvalue that dominates the eigenproblem, but doesn't give us all of the solutions, so it's not necessarily the best. Inverse iteration is targeted, but we'd have to do it multiple times. Transformation method is more promising because it would give us the full set of results, but it's actually easier to use a decomposition method, which is something that kind of naturally enables us to generate like a set of transformation or rotation operators and matrices. If we look at the timing, however, of this problem, then we know that the total number of elements computed, if it's like a number of n elements, would go like n squared. And then the number of operations per element, because we're doing sums and so on across different elements, goes like n over 3 on average. So then the overall scaling is the product of those two, which goes like n cubed. So that could be expensive if we have a really big problem in 3D. However, if we said that we're willing to accept that we don't necessarily need every single solution, but we only need the first p solutions, and we can assume that p is much less than n if it's a large problem, then we could say that storage actually would only scale like order of p times n instead of n squared. And the work that would be needed, going back to the earlier case, would by simple math be order of p squared times n. So for large n, as n goes to infinity, still scales like order n instead of order n cubed. So this is a huge win computationally, if you're willing to do that. Now we can actually reformulate the eigenproblem to put it in a plane wave basis, and you can see very clearly here, we've written it as a complex exponential depending on the reciprocal lattice vectors. So it's basically a simple Fourier representation. And then we can actually like write HK as a sum of the B's times the plane wave basis that we had earlier. And so then that gives us something that you see on the right-hand side, which goes like a complex exponential of the sum of mj times nj over capital Nj. And that's nothing more than a discrete Fourier transform, which is very good for us because it's computationally tractable. Although if we used like a normal DFT, that would go like time of order n squared. If we use fast Fourier transforms, then it goes like n log n, which is very close to order n. So that means that we can use Fourier transforms and inverse fast Fourier transforms to very quickly both do calculations in the natural domains where they should happen. So in other words, we can multiply the curl operator in Fourier domain, and then do an inverse Fourier transform, go back to the real space domain, multiply by the inverse epsilon factor, and then go into Fourier space for that final step of implementing the eigen operator. So although it sounds like more work, actually at the end of the day, it'll be much easier, in fact. So in the next lecture, we'll talk more details about how do we actually do the solution to these kind of problems.